Continue on physical chemistry, chapter 5. We're doing section 8 right now. So the standard Gibbs energy of reaction, we're going to have the standard Gibbs energy of the reaction, standard state, at whatever temperature, is just going to be the sum of all the substance I's time of the stoichiometric coefficient of substance I, of the Gibbs, the molar Gibbs energy at the standard state, and whatever specified temperature of the substance I. That's going to be the sum over all the substance I's of nu I, the Gibbs energy of reaction, or the Gibbs energy of formation. F is for formation, temperature I in the standard state. So we get delta G at whatever temperature in the standard state. It's just going to be delta H at that T in the standard state minus T delta S. We already talked before about finding enthalpy and entropy, so now we can find Gibbs free energy. And this will be true at any temperature. That's it for section 8. Now let's go ahead and do section 10. And this will be the last of chapter 5. So let's talk about estimation of thermodynamic properties. Well, we can do that through bond energies. For example, here's a molecule, or some sort of alcohol, looks like isopropyl alcohol or something. Well, anyway, whatever this is. So we're going to oxidize this. We're going to make, what is this, a ketone? Or is that an aldehyde? Well, anyway, it's been a while since I did organic chemistry. So, what is going to be the heat of the reaction for this reaction here? Well, we're going to break it down. We're going to take the reactants, break it down into the individual reactants, break it down into atoms, and then build the products. Now, when we break a bond homolytically, that means, remember, each bond is a pair of electrons. So when we break a bond homolytically, we just say, okay, this atom gets one electron, this atom gets the other electron. Of course, that's ignoring electronegativity and so on, so it's not really true, but it's a good approximation. So we can just say, okay, the typical bond between a carbon atom and a hydrogen bond is about 415 kilojoules per mole. The typical bond from an oxygen atom to a hydrogen atom is about 463 kilojoules per mole. And likewise, for a typical carbon-carbon atom bond, be about 344 kilojoules per mole. And for a typical carbon-oxygen single bond, it's going to be about 350 kilojoules per mole. And then a carbon-oxygen double bond, well, let's say, is about 750 kilojoules per mole. So we can find the estimated heat of reaction just by taking the sum of all the bonds broken minus all the sum of all the bonds formed. So the change in the reaction, we're starting out with 7 CH bonds and 2 carbon-carbon bonds, and 1 carbon-oxygen single bond, and 1 oxygen-hydrogen bond, minus 6 carbon. So that's how many, that's our final. No, wait, that's our initial. Well, that's weird. We're still going initial minus final. I think this should be the other way around. Whoops. Anyway, minus 6 single carbon-hydrogen bonds, then 2 carbon-carbon bonds, and plus 1 carbon-oxygen double bond. So the difference is going to be 1 carbon-hydrogen single bond, 1 carbon-oxygen bond, and 1 oxygen-hydrogen bond, and then 1 carbon-oxygen double bond. So the estimated heat of reaction is going to be 415 kilojoules per mole plus 350 kilojoules per mole plus 463 kilojoules per mole minus 750 kilojoules per mole. It's going to be 503 kilojoules per mole. This should be, I think I might have gotten the sign backwards, because if it's exothermic, I would expect that to be a minus sign here. Anyway, so that's the end of section 10.